welcome to my first ever math research live stream. Let's see if this is actually working, since my interface is currently telling me that the video is unavailable. It's not exactly an auspicious start, but let's see if I refresh if things will be better. Alright, well, I can see myself, although I think that it's static, so we're just going to have to hope. Oh, it's improving. Okay, great. So yes, welcome, or welcome to the YouTube recording of this if it's after the fact. I'm very excited to be here today, and I'm basically just going to be doing math research live. Now, it's not meant to be a lecture, so you know, you can ask me questions in the chat. I might ask for maybe like which thing people want to see or whatever, but you know, I'm not going to just lecture at you. I'm going to kind of show you what like the real live process of me editing a paper looks like, and yeah, and just feel free to ask whatever, make comments. In the pinned thing in the chat here on Twitch, or if you're watching on YouTube, I'll post in the video description. There's a link to the paper that I'm going to be editing, but you know, it's not a lecture, so there's no big rush. Feel free to ask whatever. I'm also happy to talk about things just related to doing math, the software that I use, whatever. And I'm also going to be doing this probably every week for a while, at the same time, every single week. So hopefully this is a good time for you. It's a good time for me. And I won't be doing the same paper every week. I'll keep it fresh and do some different stuff from time to time. All right. Well, I guess I'll just dive right into it here. So again, you can see in the description, you can see the paper that I'm going to be editing today. And so here, I already have it open. I've been using Overleaf, which I have some mixed feelings about at this point, to be honest. Like, on the one hand, I do really like that I can collaborate with people online with this. I think that's really nice. I don't really love that they've been pushing the AI writing stuff pretty hard, because I've always found such tools to actually be a little bit irritating while I'm trying to write. I have heard from people that sometimes they are able to guess a formula correctly or something, but overall I can't even stand to write an email with them, so I think that that's probably not something that I'm going to be using. But yeah. I won't spend the whole time complaining about Overleaf, though. So here, let me maybe see if I can zoom this in a little bit more. So I have a diagram of some different things that I'm looking at here. So this paper has been taking an unusually long time to edit, and one of the things that has been taking a long time. Well, I guess I'll tell a little bit of the story. If you really want to hear the whole background of what's going on with the paper, you can either ask me in the chat, or you can watch one of my YouTube videos about it, where I give an actual lecture about it. I'm not going to just like lecture at you by default, you know, like the way I normally would. I'm just going to kind of dive into the middle of it. So what's going on here is that, like, I had this paper, and there was a gap in the main theorem of the paper. And so I really wanted to get this paper posted and, you know, try to get a job when I was finishing up grad school. So I was like, okay, I can probably fill in that gap, but it's going to take some time, and I don't have that time. So I'm just going to submit it and see what happens. Worst case scenario, they ask me to fill in the gap, and then I do, and it's fine. Well, what happened was that the reviewers did not notice the gap in this proof in the paper, this part that I had skipped over, and so I actually pointed it out to them after I had the paper accepted, and they wanted some other revisions. So then I went back to them and I said, okay, like, you know, these revisions can be done, but also I left a gap in the main theorem in the proof, and you didn't notice it. So I spent some time fixing that. But then what happened was I think they were a bit annoyed with me, and they said, okay, well, we see that you've been messing around with us a little bit here, and so we would like you to actually show us that all of these things that you claim to be functors are actually functors. And so this diagram is the result of starting to actually write that out in some more detail. At this point, the paper is 60 pages long, I think, and by the time it's done, I expect maybe more like 80 possibly, but, they want the details, I'm going to give them to them. So it's been taking a long time to finish adding all of these details because, I'll do some of it and then I'll be like, I'm burned out on doing this right now, I'll do it more later, and it's been taking a while. So let's see, so at the beginning of just doing any of these things again, I didn't prep myself, so I'm really just jumping back into this now after not doing it again for a minute. So I have to figure out what it is that I'm supposed to be doing. That's always the first thing, especially on something big like this. So, my goal is to describe basically all of the arrows in this commutative diagram. That's pretty much what I'm doing right now. Some of these are very well-known things. Like, for instance, we can view every Riemannian manifold as a metric space in a functorial way. That's, pretty well understood. Other things are things that seemed obvious to us at first, but now are not so obvious. Or maybe not so obvious, but our reviewers aren't letting us take as so obvious. And so I'm somewhere in the middle of doing that process. So let's see what my options are as far as doing this. So let's see. So one thing that I do to make my life easier is I include notes for myself where I say that I need to do something. Like here I said I need to redo this outline once the paper has been rewritten. So that's a thing that I need to do, although obviously that's kind of a last minute thing to do. I don't really have to do that right now. But if I scroll through, hopefully I should find one of the next things that I have to do. As you can see, this is already getting quite long. And that also exponentially increases the rewriting process. In case you're not familiar, a lot of writing is rewriting. Oh, PDF rendering error, that's nice. Let's recompile. Overleaf is angry at me. Well, anyway, that's having its time. The other thing I can do is I can also search for, I often will say if I can spell continue correctly, let's see. Continue, no, still can't spell continue correctly apparently. There we go, continue, okay, continue our picture. Now, sometimes I write continue here, but I can also search for the command that I issue to myself. Alright, so I have something that says finish this. What's that going to be like? Where is this? Oh, okay. So, I'm actually in the middle of a proof, which gives me something to do right away. So let's see. I have something that's supposed to be a functor. I have to actually show now that this is a functor. Well, that's going to be quite something. So, let's see. I claim that this smooth severance functor is supposed to be a functor. And so what is this thing supposed to be doing? Well, it's supposed to be taking an n-dimensional pseudomanifold, so something that looks like it's made of some triangles, that kind of looks like a smooth thing, and it's making it into an actual smooth manifold somehow. So let's see what we can do here. I need to show that this is a smooth manifold. It looks like I have that. Okay, so I've already shown that it's a smooth manifold, and now I need to show that the transition functions are smooth. So let's see. Okay. Okay. Yeah. So this is something that I have to do by cases, and in order to do it by cases, I have to draw pictures. Let's see. Oh. Maybe I want itemized. No. This enumerate. I don't know why I labeled these as 1 and 2 here. That's making it actually not look very pretty. Let's see if we can make that look a little bit nicer. I'm trying to look at this list of things and see if that'll actually be nicer looking for me. Yeah, now it has the 1 and 2 in parentheses. That's good. That's a nice thing. Oh, and I did the same thing down here too, I see. Oh no, but this is because I want the label to be 1A and 1B. So I think instead, maybe I actually want itemize. It's a common thing where, can't choose between enumerate that just labels them with numbers right away, or itemize that lets me give them names. But let's see if the 1A and 1B come out pretty. You're really in for a time when you have a proof that has like part 1, part 1A, part 1B, and so forth. Let's see, did that do what I wanted it to? Not quite. Yeah, and again, just let me know if you want to ask about anything. It doesn't have to be immediately related to what I'm doing, but I'm just going to hang out and, try to get this proof written up. But, you can ask about anything that's related, including the software or other stuff that I do. At some point I'll actually be drawing stuff here, and we'll see what's going on with that. Alright, cool. So, let's see where I was at with this. This is definitely where I was before. Okay. So, I'm trying to show that these transition functions give us a smooth map. And so, I have some oriented simplex, and I'm going to have something else that has an overlapping image. Okay, I think it's time for me to start drawing a picture. Okay, so if I can find my writing utensils here. I'm also relatively new to journal, XOURNAL, so, or is it external? Am I using, am I using LaTeX? Yeah, this is tech, or LaTeX actually, yeah. Yeah, this is LaTeX, right here. So, yeah, that's what I'm using. And yeah, feel free to ask me whatever I'm using. So Overleaf is just an online platform for collaboratively writing LaTeX together. Back in the day, people used to use, well, okay, maybe not so back in the day, since this still happens, I'm sure, but people would use Git and use something like GitHub or GitLab or other such things. Like they use version control software for that you would use for programming, for writing code together. Because LaTeX is code, in that sense. And so people would use that software in order to collaboratively work on documents, and that was fine, for what it was. But it still got kind of exhausting, just because what you'd really like is to be able to see live both people working on the document at the same time. And Overleaf makes it possible to do that. I'm still hopeful that eventually there can be some some really good open source peer-to-peer kind of alternative, or at least something federated. But we'll have to see. Anything that's kind of live and interactive like that is a lot more expensive to do, especially at a small scale, using those kinds of systems. I guess maybe at a large scale it would be better, because file transfer is better, I think, using something like torrents as opposed to a traditional paradigm. But yeah, I don't know. But yeah, so the short answer is I'm using LaTeX. Yeah, and feel free to ask whatever. There's no big rush. I'm just going to be hanging out here, working on this and messing around for a few hours. And so I'm still in the first stage where I need to remind myself of what it is that I was supposed to be doing, which usually takes some time. So I'm supposed to be showing that this smooth severance thing, S-sev, is actually a functor. So in order to do that, I should remember what I claimed that it is. So here, let me hop back over to my my drawing, and I see. I need to actually be able to see my overleaf document at the same time as this, which is not something I really thought too much about before, but that's a relatively easy fix, so I can do that. All right, I'll just pop this over here. Okay, so let's see what I need to do. So first of all, this thing, whatever it is exactly, it's supposed to take these pseudo-manifolds, and it's supposed to give me a smooth manifold of the same dimension. And so how is this supposed to work? Well, if we have some, I always want to write F, gamma, if we have some gamma, which is an object of this category of pseudomanifolds, in other words, if gamma is a pseudomanifold, then what it's going to be is it's going to have a whole bunch of simplices, which you could think of like triangles or maybe some higher dimensional super triangles, that are glued together in some kind of nice way. So it's going to have these, and just to try to be consistent with the notation that I use, so I'll think about having a triangle, maybe whose vertices are like S0, S1, S2, or so forth, if it was a higher dimensional thing, and so maybe I'll say that triangle is gamma, and that's like S0, S1 through Sn. And so, well, I also want to think about maybe having an ordering on these things, and so I'll think about choosing the ordering S0, S1 through Sn. And so the way that I'm going to make a smooth manifold from this is for each such oriented thing, I'm going to have a map, which I call, I think it's phi, and then the oriented gamma, it's like gamma with a little arrow on it, and this is going to go from this bipyramid to, what did I call it? Let's see. I need to find out what I called the underlying space of this thing so that I can try to be consistent with my own notation. Oh, by the way, you'll notice that if you scroll through the preprint on the archive that's linked in the description, you'll notice that I actually don't. It's very much not the same as what I'm scrolling through right now. That's something that you might notice, and that's because I've added a lot of detail and clarified a lot of things that in that one is just really glossed over. And so right now, let's see. I'm realizing that I think I went back too far. So a lot of these calculations that I'm scrolling through right now are not in the paper as it is on the archive, and they explain much better what's going on, and I really think the organization is starting to come together a lot better. And so actually these calculations will be really helpful for me in what I'm doing next, because I actually did a lot of the hard work already. Oh, okay, this is a bit of a digression, but one thing that's kind of been bugging me here is that, like, I just have some lines that are really short and some that are really long, and like, if I left justify it, I feel like it looks bad too, and so I'm just really not sure what I want to do about this. I mean, it's kind of weird, but I don't really remember having this specific problem a lot writing papers before, where like I had such like a dramatic difference in line lengths for whatever reason. Maybe I did, and I just literally don't remember, but I'm not really sure at the moment. So that's something that I'll have to deal with at some point. Okay. Oh, so remember a minute ago when I wrote like this bi PYR thing, and I said I need this bi-pyramid. This is what it is, or maybe the higher dimensional version of that. It's like two pyramids stuck together on their bases. So I'm gonna need that for the domain of my charts when I define the atlas for the smooth manifold. Oh, you know what? It was right here, and I just wandered off because I wasn't paying good enough attention to what I was looking for. But that's fine. So actually, the underlying space of this is what I call the geometric interior of the pseudo-manifold gamma. So I'm not going to get too stuck on that right now, but basically for each of these oriented triangles or simplices, I have a map which I've already shown as a continuous map from that bipyramid. Oh, I didn't write PYR, I wrote BYR for some reason. From that bipyramid into this geometric interior of my space. Okay, so here it goes into the geometric interior of whatever that pseudo-manifold was. So, so the idea here, I guess, just to explain, because why not? So the idea here is that, so I have a bunch of triangles like this whole thing is like capital gamma, it's like something like that thing, and then this geometric interior, it's going to be kind of a shape where like, I'm going to include just like the insides of the triangles and where they touch each other, but not the outsides. So it's like if I had what I drew right here. Okay, maybe I'll add to it a little bit more. If I add to it a little bit more, maybe it looks like this. If it's something like that, then what I'll get over here, it's kind of like I just have the triangles and where the triangles touch, but not like these points in the middle. So it's sort of like I took that point and I removed it, and similarly with the other ones. So I'm kind of like poking a bunch of holes in it, like this, and maybe there's more stuff over here. So I kind of have this type of thing going on. So that's pretty nice. And so on and so forth. And then I have a map from that 3D pyramid thing, or higher dimensional pyramid, into whatever this shape is. Okay, I guess actually if I was really doing a 2D one, then this would be whatever the 2D version of that 3D pyramid is, but whatever. Heuristically, that's the idea. So I have all of these maps, and these are my coordinate charts for my smooth manifold. And so now, if I'm going to actually prove that my construction is functorial, I have to show that it's nice in the sense that it sends morphisms to morphisms in a way that's compatible with composing them. All right. Let's see. Are there? Okay, I said I wouldn't ask if there are questions, but I guess I'll just remind you. Just remember that you can ask me things if you want at any time in the chat, and I'll be happy to explain whatever in more detail. Also, just I have a totally unrelated question, or can you give me a big picture explanation or anything like that is also a valid question. Okay. So, let's see. So I have this family of charts, and I kind of remembered a little bit more what they are now. And so I have to think about having two of them. Yeah, so this is the thing. I have to think about having two of them that overlap in their images, and I need to show that their composite is still smooth. So, well, so it's like I have two of these maps. Maybe I'll scroll down here and give some heuristics. So it's like maybe here's gamma over here, and here's that geometric interior of gamma. And so the idea is like, well, imagine that I had two different things. Maybe this is like gamma 1, and this is gamma 2, and I can give them some kind of orientation, and these are two different triangles or simplices in gamma. Well, over here, you know, if I look at phi for gamma 1, I'm going to get something inside of here which kind of looks like one of those bipyramids, and maybe I'll just kind of heuristically draw it like this. It might be a higher dimensional version of that, but it's like a similar thing to that. So I'll get something like this. And I'll get a similar thing for phi gamma 2. Okay. So in general, these don't touch each other at all, and there's nothing I have to do for them because there's nothing going on. The only interesting situation is when these two images actually overlap with each other. And so what I had started to write out in the overleaf document before I drifted off to whatever else I was doing, what I started to write in the overleaf document is how can these two different things overlap with each other? And so, well, let me just go back to that to remind myself of what I already observed. Either gamma 2 is just a reordering of gamma 1. So that's definitely possible. So let's see what happens when gamma 2 is a reordering of gamma 1. So that's like saying like maybe gamma 1 is like, you know, S0, S1, S2, and maybe gamma 2 is, well, some reordering of that. Maybe it's like S0, S2, S1. Well, what's going to happen is that, well, for gamma 1, we'll have something like this is our S0, this is our S1, and this is our S2. Maybe I'm not following my own conventions here. Let me see. Oh, yeah. So I think that actually the way I'm supposed to be doing this, because I didn't remind myself, is that let's go back and look at definition 7.2. Okay. So I see. Yeah, okay. So actually, my picture was slightly off, and so now I can correct that because I've reminded myself of what this is supposed to be. So the idea is this. So S0 is like the tip of this thing. That's the idea. So this is S0. Maybe this is S1. This is S2. And so this is what I called S0 prime. There's always going to be an S0 prime in my setup because it's supposed to be a pseudo-manifold. So the idea is that inside of here, it kind of just looks like a little piece of the plane or of some higher dimensional space. And again, just feel free to stop me anytime if you're curious about anything, you want me to talk about whatever. It's not a big rush, you know, I'm just hanging out and trying to remind myself of what it is that I was supposed to be doing here. So I need to prove that this construction, one of the many constructions in this paper is functorial, and I'm on my way to remembering what my job was to do in the first place. Okay, so that's what would happen if gamma 1 was S0, S1, S2. And, well, if gamma 1 was S0, S1, S2. So if gamma 2 was S0, S2, S1, then it would be like this instead. Like the order would be reversed. So that's one way that they could overlap with each other. So that's definitely possible. But if it's S2, if it's S2, S1 instead, well, that's still, I mean, it's still the same edge of the same face there. Or it's still, well, yeah, I guess that's what I want to say. It's still the same edge of the same face. So if gamma 2 was just a reordering like this, then this should still just be S naught prime. In other words, what I figured out at this point is that if gamma 2 was actually just a reordering of gamma 1, where I didn't change the first thing, then it looks like these two things should just be the same shape, but kind of mirrored or flipped somehow. And so that's actually the first case that I was considering here, or back where I was before. Let's see, back over here. Oop. Okay, so the first possibility was that gamma 2 is just a reordering of gamma 1. And so there are two possibilities then. Either the S naught thing was fixed or it was not fixed. So in the first case, this is what I'm saying, the images of both of those maps overlap with each other. And so, let's see. Well, then I have a map from that bipyramid thing to itself, and I have to show that that map is a smooth map. So maybe I'll do that first. So in order to figure out what this is, I need an actual formula for what this composite thing is here. Oh, it's too much highlighting. Whatever this composite thing is down here, I need a formula for that. And so, well, I better go figure out what the formula is that I need. So, let me maybe go back here. Let's see. Okay, so I need my formula for this sever chart, and of course, this is a bit of an involved definition as well. So let's see if we can extract what we need from this. All right. So maybe I'll move this back over here, and I'll see if I can figure out what I need to actually compute here. Okay. And feel free also to comment if you would like. I mean, are people's is this like totally wildly unfamiliar to people? Do I have like more mathy people here, computery people? Like, feel free to just, make your existence known and let me know what's going on. If there's something interesting I can talk about that's, tailored to what you're interested in while I'm computing this, then that's would be a cool thing too. So at this point, I have figured out that what I need to do is I need to figure out if I have that phi gamma 2 composed with phi gamma 1, and I'm just looking at the case where gamma 2 is a reordering of gamma 1, where the first thing, this S0, is fixed. Oh, I see. So this is just some kind of spam, apparently, so I can probably deal with that. Yeah, so... Oh, okay, here's something that's not spam. I'm happy to discuss these things with people who may not be experts in everything that I'm talking about. I think one of the things that's cool about doing this and why I'm excited to do it more is that okay, I can't 100% say for sure. Who knows? Maybe I'm thinking that I'm more awesome than I really am. But I feel like watching me do this and refigure out what I'm supposed to do and draw the pictures that explain what I'm supposed to do is going to be radically more understandable than the final product that will be on the archive. For at least 4 people, maybe. Okay, I don't want to say this. I do want my paper to be readable, and it will be. Like, there's no question about that. But, like, that's, like, readable for experts who are willing to sit down and compute all of this stuff themselves. Like, this type of stuff you've got to draw pictures for. And it's, like, this sociological thing where it's, like, if you don't know that you need to draw pictures, like, really simplistic pictures like this, I mean, relative to the complexity of the topic, in order to understand, then, like, you're just not gonna be able to do it. And so it's not like really a secret, but it's like there's all these little things where it's like if you don't know what to like try to figure out how to do it, you're not going to be able to do it. And then if you do, you're going to be doing like 17-dimensional geometry like it's no big deal. And so it's just that having that notation is very helpful for being clear and precise, because like it's easy for me to lie to you without having to give you like the full technical detail, like just drawing this stuff and saying, oh yes, I understand it and I can do this in 12 dimensions. Like, it's really easy to lie to yourself and to other people about whether you really understand what you're doing. Because you want to think that your intuition is correct, but it might not be always. And so having that formal, careful verification, even without doing like the machine verified proof kind of thing, it is really important. But this is a critical step. Like if you didn't know how to do this, you can't read any of it. So like that's definitely, I think that's a really important thing. As far as the next comment, I see. So we have someone who may remember the definition of a functor from memory. Don't remember what charts and atlases are, and yeah, I wouldn't. I don't really trust visual proofs very much myself either. It's definitely true. So this is, I guess, to answer the next question. Oh, now I'm getting a bunch of questions. Cool. So to answer the next question, this is exactly that. If you saw the link to the preprint in the at the top of the chat there that I pinned, it says as much in the abstract for that. And I'm editing this paper to make it nicer. So yeah, it's a higher dimensional. It's going to be a higher dimensional version of that thing. Maybe I'll just mention briefly. I guess I'll say. Okay, maybe I'll say a little bit more. So it is a higher dimensional generalization of this thing from an earlier paper where finite groups, like the symmetries of finite objects in some sense, maybe just to make it simple, you can take something like this is a digression now. Let me just pop over. So you can take something like maybe I'll just do a new page even. That'll be nice. If you have like the square, maybe you can think about the square having different symmetries. Like you can reflect it over this axis, you can mirror it. Or you can, rotate the square, maybe 90 degrees, you can rotate it around, and there's all these symmetries. Yeah, it's digression time. And so you can get a whole collection of those symmetries, and you can think of each of these symmetries as like some kind of object in its own right. Maybe tau is the reflection that way, sigma is like rotating the square around a quarter of the way, and so forth. You can think about composing these two, so like you can think about doing tau and then doing sigma. We don't usually write a plus sign, but it's something like you can combine them to make something where, you reflect and then you rotate. And so like, maybe if it was like A was over in this corner, you reflect and it moves it over to this corner, and then, if you rotate it, then you're going to move it over a step, and so like maybe you get something that ends up over here. It seems good. So you get that sort of thing, and so this is maybe what you might think of as like tau plus sigma. Although again, we usually don't use the plus sign just because of conventions. But you can think about, like, there's a whole object that is the symmetries of the square, and now I'll get a little bit controversial, and I'll say that this is D4. I know some people call it D8, but I'm going to call it D4. The dihedral group of order 8, which is why some people think this is evil to call it D4. But, you know, that's some kind of algebraic object, and what had been done previously was you can take this and you can somehow or other make this into an actual object. And it's usually, I mean, it's always going to be some kind of two-dimensional manifold, like maybe it's like a donut with a couple holes, and maybe there's a couple spheres, and so on and so forth, whatever. So there's some kind of systematic way of making shapes like that out of such algebraic structures, finite groups. But when you do this, you actually get a little bit more than what I just drew here, because really what you're actually getting is, like, it won't be a sphere like this. It'll be like maybe like some kind of you know, cube or other type of object that's made out of regular pieces. You know, maybe you'll get a pyramid, and topologically that's a sphere, but it's not, you know, literally a sphere. And it's harder for me to draw, but you can actually get shapes that look like these donut kind of shapes, or tori. Okay, it's a terrible torus drawing. I'm gonna have my topology card taken away from me for that. So you'll have something where, you know, maybe this donut will actually be made out of little pentagons that are all stuck together, and so forth. So that was like the original thing that this is based on. So the thing that's different about our construction here, or the one that I've just been talking about, or working on the paper for, or whatever, the thing that's different here is that it turns out that so groups have what's called associativity. If I have like three symmetries, I do symmetry A, symmetry B, and then I combine those, and then I combine it with symmetry C. I always get the same thing as if I combined B and C, and then I did A. It's kind of like saying, the order in which you group them doesn't matter. It works the way that multiplication normally works, you know, for the integers or whatever. Somehow, that I won't get into maybe too much, somehow having this gives you these nice what are called tessellations, like kind of like having the floor tile and the, you know, you can have like maybe a square tessellation, you know, or you could have like, you know, like maybe it's a little harder to picture, but you could kind of think about having a tessellation made out of pentagons, you know, instead, or, yeah, it's harder for me to draw too, or all of these other types of things, you know, maybe triangles. So somehow having that kind of nice pattern comes from having this associativity. But, so for that case, making these surfaces from finite groups, you always get the repeating surfaces made of repeating patterns, like a tile floor. So that's true. However, in the case that I was just discussing, it turns out that you need to replace groups with something that are not groups anymore to do the higher dimensional version of this. If I want to get, instead of things that are made out of like like donuts and spheres and things like 3D, but they're two-dimensional manifolds because they're made out of a like you could think about taking sheets of paper and kind of gluing them together or folding them. So it's like a 2D thing because like the outside is flat. Think like a beach ball as opposed to like a solid ball. It's more like beach ball as opposed to bouncy ball. So it's like a 2D thing. And so you could think about doing the 3D version of this in the sense that the surface of this would be like a three-dimensional thing. These are harder to picture, but you can define them and it can be done. So the thing is, to do that, you have to replace the group with something that is not a group. And you actually need to replace it with something that actually has a ternary multiplication rule. Turns out the binary situation isn't very helpful for us here. You need to be able to multiply three things together in some sense at the same time. But okay. But unfortunately, it turns out that you don't really get very nice pictures. Oh, well, I think that we're receiving a visit now, so maybe let me take a minute for that.
Say hi.
Debbie.
Say hi. Say hi.
Debbie. My dog and my partner are visiting me. Hey, buddy, do you want to say hi to everyone? No, he thinks you're going for a walk.
I'm gonna go outside laundry, and then you can hang out with him, and then I'll take him.
Oh, okay. All right.
So I'll be right back.
All right. So my dog is a good meeting dog. He's really on top of things. He really keeps things, organized, and he just really knows what's going on. Oh, Buddy. His name isn't Buddy. I just call him Buddy.
Oh, actually, I need your laundry key. I forgot.
It's just the code. I left the deadbolt unlocked. Yeah. So maybe he'll come over and properly visit us at some point. But I think, oh, Dobby, come here. Come on. All right. He's too excited by what else is going on. If I don't pay attention to him for a minute, he'll really want to pay attention to me. Like, I'm actually surprised because normally, like, if I am out here, like, having any kind of meeting or anything, and he's in the bedroom, like, when he sees me again, he'll, like, flip out, and, like, it'll be really crazy. Anyway, he's our mascot here. Maybe he'll come say hi at some point. What are you doing, bud? No? Okay. Alright, well, anyway, so maybe he'll visit us more later. So the story I was telling was about getting these tessellations, and so it turns out that although in this case with the groups making surfaces, it comes out to be very nice. In that case, it's this very nice family of these tessellated surfaces. In the higher dimensional case, digression squared. Thank you. Yeah, that's right. So in the higher dimensional case, it turns out that having associativity like this is actually very bad. It turns out that you don't get anything interesting at all if you have associativity. It just doesn't work. And so because of that, we don't want to consider just the associative examples of whatever our higher dimensional version of groups are, because they're just not going to be very interesting. They're not going to give us shapes at all. They're just going to give us nothing. And so we need the non-associative version of those things. But the thing was that these nice tessellations, they came from having that associative property, and so we have to give up the associative property to go to higher dimensions, and then we don't get we don't always get tessellations as a result of that. So unfortunately, the idea of building surfaces from finite groups does generalize to higher dimensions in some way. Unfortunately, it doesn't generalize along with the tessellations. You don't get the regular repeating patterns. They become irregular in the sense of maybe around some points it kind of looks more like a pentagon. Oh, that's a really unpleasant looking pentagon. Let's try that again. So in the higher dimensional case, you don't just get regular patterns like this. Instead, you get things that are around this point, you have maybe 4 triangles or something. So it looks kind of like a square, but then there's another point, like say this one, where it's not 4 triangles, but 6. And there's not really any kind of regular pattern in that sense. And this is just inescapable. You need to have this kind of irregularity in order to accomplish the same type of thing in higher dimensions. I can prove that to you rigorously, but that's kind of the idea. So we don't get the tessellations, but we do actually get shapes. And the nice thing about this is that even in 2 dimensions, it actually is still not known whether if you give me some kind of two-dimensional surface like this, say like a donut with a certain number of holes, what is not known, I see I've made the one that's like a fidget spinner, that's nice. You know, if you if you choose some number of holes, like probably for 3 you can figure it out, but imagine you had something like this, but it had like 100 million holes instead. Oh, what makes that an irregularity? It's because, when you do this construction, okay, to go back to like why is what I just drew an irregularity, it's because when you do this construction, like I'll illustrate this with the square tiling. In the sort of the traditional thing for finite groups, when you do this construction, you're always making the things out of triangles. Like fundamentally, they're always made out of triangles in the 2D case. And so what's happening is just that if you look at any specific, specific point here, well, it's going to be that there's like a square of triangles around it, like this. And so these squares made out of triangles, those are the squares in the square tiling. And similar for other kinds of tilings. Like it's just, yeah, I mean, it's just that this is what's really going on. So we think of that as being a square tiling. And of course, I'm not going to draw the whole thing, but you can imagine things like this glued to themselves in order to make like some kind of ball or donut with a bunch of holes or something like that. That's, you know, that's why it's a square tiling. Okay, there's a little bit of detail I didn't mention, which is that there's 2 types of vertices in this. There's like somehow we know which ones are supposed to be the middle of a square versus which ones are supposed to be the edge of a square. Maybe I won't go on about that right now, but we know that. So we know that each of like the ones I drew as the middle of like one of the 4 little squares is supposed to be a middle vertex. So over here, it's possible that yeah, I'm glad that if people are having fun, then that's good. Yeah, right. So even if we know, or well, what am I trying to say? So if we know that, say this one that I'm making darker here and this one that I'm making darker here, you know, maybe it's possible to have something. Okay, well now I'm realizing I want a better example. So here, let me draw something that's a slightly better example than the one that I just drew to make it clearer that it's an irregularity. So maybe we have something that looks like one of the squares from the original thing. So this is supposed to be that middle vertex. We know which ones are supposed to be the outside vertices, and this is some kind of square. It's possible that over here there's another middle vertex that is this one that I'm making bigger, and it doesn't have 4 things around it, but it has maybe 6. So this type of thing is not possible in the group case, but it is possible when you have a non-associative thing. And in fact, it's basically you have to have non-associative things in the higher dimensional case. And so you end up getting things that look like not a tessellation of the same shape over and over again, but some kind of more complicated thing where you have shapes that have different numbers of sides glued together. And this is kind of like inescapable. You kind of have to have this if you want to go to higher dimensions. In 2D, oh yeah, so that was the other thing I was going to say. In 2D, this is also actually a helpful thing to allow, because allowing non-associativity in 2D allows you to find, to make any possible shape that you choose that it's like this out of some finite, not group, but finite quasi-group. So if you drop associativity, you can make all possible 2D shapes like this in this way. For groups, it's not known whether that's possible. So already when you drop associativity, you're getting results that are much stronger than if you were to demand it. But you don't get those nice tessellations. So that's kind of the trade-off. Yeah. So, oh, there's another question. Are mathematicians interested in shapes, or do the shapes serve as a way of making making the abstraction tangible? So, if there's two things that I'm really into, they're shapes and numbers. And I think that this is a little bit of a personal philosophical kind of thing. So, like, yeah, how do I want to say this? You can think of, shapes are themselves a kind of abstraction, I suppose. I'm glad the previous explanation was appreciated. There's a little bit of a lag. Like, when I say something, it takes about 30 seconds or so to reach you wherever you are in the world. So, but yeah, I'm glad that the previous explanation was appreciated. Thanks. But yeah. So like for me, I like abstraction. I was the undergrad category theorist. I was the kind of person that just wanted it, abstraction for its own sake. I thought it was fun, but even when I was an undergrad, I realized, making abstract things tangible, making shapes out of abstract, algebraic structures or other kinds of abstract concepts, so to me it kind of feels like there's like this sort of like, intangible like world of abstractions, this like Platonic realm somewhere up there, outside of our, concrete existence here, and taking something that's like just an abstraction, like the symmetries of a shape or something, and pulling it down into our level of existence by making it into an actual object that you can hold in your hands, or that an 18-dimensional alien could hold in their hands, or whatever. It feels like you've accomplished something in the sense that you can understand, you can understand things about the shape, and that helps you to understand things about the abstraction. But it really goes both ways. Sometimes it's really hard to get a good visual intuition for shapes, especially when they're higher dimensional. And so, in that sense, it's also good to know how shapes correspond to abstractions. I think somebody else's dog is very upset now. I don't know if you can hear that. Yeah, I mean, it's also helpful to have the abstractions correspond to the shapes because, for instance, if you know that you can make any shape of the type that you want to out of some kind of algebraic structure that has a certain, some nice properties, then you know that you could just study those algebraic structures instead of studying the shapes. And the reason that you would want that is because, like, in many cases, it's easier, say, to like work with algebraic structures on the computer with rules for like how to multiply or combine things together than it is to work with shapes on the computer. I mean, if you think about it, how are you going to actually describe like a circle to a digital computer? Like, what is that supposed to be? And whatever way you come up with of describing it, especially if it's mathematically precise in the sense that it really does contain, the information that you, like, it's not just some, blurry JPEG of a circle or something, but if it actually contains the information that you'd want about what a circle is mathematically, then you're not going to be able to do that without doing some kind of algebra. Like, that's like, it's not gonna happen. And so it's really a lot nicer to work with these things on the computer when you have that abstraction. So yeah, I think that it just it really depends on your inclinations and your philosophy as to whether we like the shapes themselves or just like the fact that they can represent more abstract things. So I do actually have some experience. Is everything okay?
Yeah, there was just some dogs. He was meet and greeting through the fence. All of them barked at each other because that's how dogs are through the fence.
Oh. Oh, I just assumed that. Wait, did he bark or was it just the other dogs?
Everyone barked.
Everyone barked. I just assumed that he couldn't be barking because he's
so good.
Yeah, because he's a good little.
Well, it was two of them and one of him, so he
Aw.
probably felt a bit threatened.
Are you okay? Hey, Dobby, do you want to say hi? No, he's still too excited.
I know you were probably expecting to get some actual work done, but we got questions.
No, I really like answering questions, and yeah, it's a lot of fun. This is actually what I was hoping would happen. And who knows, maybe I'll do some more work later too. I'm still doing this for 2 more hours, so yeah.
Sorry to interrupt your stream.
It's okay, sweetie.
Do you want him out here, or do we take him back?
I'm good either way.
Where do you want to be? Do you want to go in there, or do you want to stay in here?
He's just gonna wag his tail and look at you.
Alright.
Alright. So, I guess I'll try to answer questions in the order that they've appeared. So have I used lean or other proof assistants? I have a bit. So I am most familiar with Coq, although I wouldn't say I'm like a complete expert or anything, but it is something that I would like to get more involved with. I have a project where a collaborator was formalizing stuff in Agda, and so we may get back to that at some point. It's on that part of it at least has been on a bit of a hiatus. Let's see. And I have also used some automated theorem proving tools, So in universal algebra, well, there's tools for just kind of more directly doing calculations in universal algebra. Like there's the universal algebra calculator, but then there's also stuff like Prover 9 and Mace 4 that are like automated theorem provers or model checkers, which I've used a bit as well. My postdoc advisor is actually a lot more, he's been doing that stuff for a lot longer than I have, and so it's been cool to get to see a bit about that. I had an interaction which, if you search or scroll back for a while, you can see last summer. I was talking to Terrence Tao about this on Mastodon, because I think he was preparing for the talk that he gave at the joint meetings this year, and I was like, or maybe it came up from something else, I don't know, but I was like, it's true that, there's a lot of these, general kind of, proof assistants now, and I mean, there have been, it's not like Coq is brand new, for instance, but there's also been, things in universal algebra, especially like Prover 9 and Mace 4, that have been big things for a while that are very useful. It's part of, maybe not the whole reason, but it's part of how, if you read some of those papers, they'll say, and then we're going to need to use this identity, and it's like an equation that takes up like 6 pages, and you're like, how did people actually come up with that? Like, where is that from? And sometimes it's just because that's what works, and that's what came out from Prover 9, but that's what it is. So yeah, I guess the short answer is yes, I have used some of these things. Yeah, I don't know if I feel quite as confident doing that live as I do doing math, like old school math live, but I may try it at some point, depending on people's interests. Oh, cool. Nice. Yeah, so, I see that, so somebody here got more into Coq and dependent, or got back into math by using Coq and dependent types, and the rest has been history. That's really awesome. Yeah, I'm still not super fluent with any of these things yet. Like, I can use them, but it's not it's not like every single project or every single day. But yeah, it's definitely something I would like to be more familiar with. yeah, and like I'd like to check out lean. I know a lot of people have been into lean. You know, it's just kind of an interesting time that we're in. If I can like philosophize a little bit, I guess, because like as you can see from what I was just doing to work, like in principle, I could try to like formalize everything that I'm doing and seeing if I could get some of those proofs automated. I mean, like if I really wanted to go like all out, maybe I could even try to get like an English language description of the thing from those tools. But yeah, but I don't know how realistic that is at the moment, or maybe even ever, but especially at the moment, I don't know how realistic it is for me to automate the production of something that's this intricate. It seems like it would be extremely brutal to actually try to formalize what I'm writing down right now. But who knows? I mean, people are building libraries all the time, and maybe in another 10 or 15 years, we'll be in a place where it's much more doable, and this will seem like I'm just kind of you know, grinding through tedious calculations compared to, you know, what it'll be like then. But I'm really not sure. I mean, people have been saying that computers will do these things to mathematics for a long time, and so far, even though we have all sorts of tools, that hasn't really replaced the need for me to do like what I was just sitting and doing at the beginning of the stream. It's not really stopping me from having to do that. It's not like I'm just doing it the old school way just to be old school. Like it's really necessary, at least to my understanding at the moment. But yeah, I mean it's really awesome that we have these proof assistants, and I'd like to integrate them more into my workflow as time goes on and as it's appropriate. Yeah, I mean, I know too. I've seen like people who are much more fluent with these things, like especially in category theory and areas that are very much like general nonsense. You know, you just kind of use the type to determine like what you're supposed to be defining or computing or whatever. It's really wild the amount of stuff that they can automate for you. Like it's really nice. But I do think it may be a little bit area dependent. Category theory is kind of designed to be automatable in this way. And although I'm a big fan, I don't know if literally everything can just be reduced to doing such calculations. Although I know that's probably heresy. So if any homotopy type theory people are watching me say this, you know, I'm definitely canceled at this point for sure. All right. Anyway, maybe I'll stop ranting about that for now. Yeah, I'm really loving all the feedback that I'm getting. This is really cool. So there's a question. Oh yeah, I see. Yeah. Good proofs happen the old school way before happening in formal rigor so far. Yeah. Actually, okay. One more thing about proof assistance before addressing the other question. With whatever generation of these things, I think there's still a lot of issues of like if you get a proof that is a proof to a statement that you didn't know how to prove before. You're going to have to do some kind of translation where like you don't it's not like it's going to be explained to you like the way I'm explaining what I'm doing right now with pictures. Like it's going to be a sequence of symbols that have no inherent meaning to you, and you have to like unravel and decide like what it's supposed to mean. And it's not like it's going to be the most eloquent thing. It's just going to be something that works. And you're going to have to try to figure out what is going on with that, and it might just be indecipherable, except that it just happens to work. That's kind of the nature of these things, though, as far as I understand it. Yeah, but so at one point do math students go from proving if G is a group, then G is a group, to understanding all the stuff going on in my paper? Okay. Well, I'm assuming that if G is a group, then G is a group is meant to be kind of just an example of something that's like supposed to be an easier thing to prove. Because things are what they are. So no deep philosophy there. It's it's a tautology. But yeah, I mean, so everyone's path is different. the way that classes are set up, like, in primary school and university, whatever, the way that things are set up, and maybe even the way that people like outline these things on courses, online or whatever too, you think that there's like an order that these things are supposed to go in, but like that's not really it's not really how it is. There are certain things that you kind of need to understand before understanding other things, but like it's a lot more of a personal journey than people realize at first. And so like for instance, I had some exposure to abstract algebra as a teenager, but I didn't actually get into it super much until I was in my late teens. And I didn't have like a full course or anything, but I, had seen a little bit of abstract algebra as a teenager. And so when I was in my late teens, I got a little bit more interested, and I started to know about things like what groups were. By the time I was 20 or so, I knew what groups were, and I knew the basic theorems about groups and that sort of thing. And then while I was an undergrad, I started thinking about ideas that would lead to this paper, but it wasn't quite to this level of like detail or specificity yet. So I like to think about if you can think about a group as having maybe its multiplication is f, it's a thing that takes pairs of things from your group and gives you another thing from your group. And so then, what I got interested in thinking about was, normally we think of f as like a multiplication, so, f of xy, we normally write this as like x times y instead. And then we normally, assume that, we have a group multiplication or at least something associative, so that x times y times z is x times y times z. But because I liked abstraction, I was like, well, why should I assume that, why should I assume that that's the case? Why can't I just have any function that I wanted that had this type, that took pairs of things to another thing? And so, of course, one can. And if you don't bother with this or any particular axioms, if you just have a function like this, that's what's called a magma. And you're welcome to try making a joke related to this in the chat if you want to. I've heard many of them at this point. So I mean, yeah, you're welcome to come. You're welcome to come up with one if you want, though. But yeah, I believe so. So I've heard what do you call a structure that has a single binary operation, when it's above the ground, it's a lava or something, something like that. Set with a whole bunch of binary operations all over the place is a volcano. I know. Oh yeah, I know. It's pretty bad. There are actually things called isogeny volcanoes. So I actually read part of a paper that someone pointed out to me on Mastodon, I think. If I remember correctly, and I want to say it was algebraic geometry. Yeah, elliptic curve stuff. That's right. And so I'm not much of an algebraic geometer actually, but I had started reading this, and because I get into lots of things and I get interested in lots of things, and feel free to scoop me on this one, I guess, if you want, because I don't think I'm realistically going to get to it, at least not by myself. But what I was thinking when I was looking at this was I've got to figure out how to put a magma structure on the isogeny volcanoes. I need to figure out what type of objects these are, and then have a morphism from the product of one of these things with itself to itself. And then that'll be an isogeny. Oh, if I can spell it correctly again, I spelled it correctly the first time, of course. that would be an isogeny volcano magma, and then we can just really start going to town with that. Oh, well, of course, that's just the first step. The second step is going and finding a geologist who specializes in volcanoes, like a volcanologist. And then we have to see if the isogeny volcano magmas can have some kind of application in the study of volcanoes, because then, we'd have, we'd have volcano isogeny volcano magmas, and I think that would be a really great, thing. Oh yeah, thanks for posting the isogeny volcano paper. I assume that that's what the archive thing is that was just posted, and that's awesome. Thank you. Okay, I'm curious about the comment in the chat about sticking associativity where it has no reason to be. Can you elaborate on that at all? Like, what? Like, can you give an example of something like that? Associativity really is all over the place, and it does kind of make structure appear in just about everything. Okay, well, while we're seeing if that's gonna take place. Oh, I should finish this story. I had another story. Oh, okay, and now I always. Oh, okay, all right. Well, there's a new thing in the chat. So, even more fun. Oh yeah, a volcano is a graph theoretic definition. That's right. I read part of this paper, and then I did not actually finish going through with this idea. That's right. So volcanoes are graphs that are defined somehow from elliptic curves, and so having a morphism like this. No way. Okay. All right. So I have a couple things to say. So first of all, so if V was actually a graph, maybe even a graph that was split into designated levels, then like the product of these things makes sense in the category of graphs, or graphs that are so partitioned, or that type of thing. Oh yeah, thanks for joining us. It looks like there's work to be done elsewhere, but yeah, thanks for checking it out. I mean, you could of course like define like the product of two graphs, and then think about a homomorphism to another graph, and that's actually very related to some artificial intelligence work that I'm also doing at the moment. But maybe I'll leave that there for now. But thanks for mentioning that. So sticking associativity where it has no reason to be had something to do with saying, like, what if you're asking for this? Like, what if you're asking that f of AB is actually in AB? So that's an operation that has this property. I don't know all of what you did with it, but an operation that has this property is called conservative, where the result has to be one of the elements that you had plugged into it to begin with. And actually, I studied families of particular kinds of conservative algebraic structures in my first single author paper, which was on multiplayer versions of rock paper scissors. And maybe I'll pop that into the chat just to share that with you. I'll give you the archive version so that you can actually read it if you want to. So I'll post that in the chat. So that's multiplayer rock paper scissors, and I actually studied families of certain kinds of conservative algebraic structures in that. So you can go find videos of me talking about this paper on YouTube too, but basically I got stranded in Yosemite National Park in 2017, and and don't tell anyone, but I lived in a cave for a little while, and so I wasn't doing so well financially, and so while I was living in a cave there, I wanted to explain to my friends that I was really into abstract algebra, and I needed a good example of the kinds of algebraic structures that I was interested in studying, and so I thought of using rock, paper, scissors. But then, of course, I wanted to figure out what a good multiplayer version of rock, paper, scissors would be. And so, the rest was history, and I ended up writing this whole paper. It's my first single-author paper that I published, and it was a really good time. And it was actually a good cave, too. It was a really good cave. I could get Wi-Fi there. Or not Wi-Fi, it wasn't Wi-Fi, but it was like the wireless internet. It reached over there, and it was only like a 6-mile walk into town. It was beautiful. It was great. I'm sure if I had tried it during the winter, I would have died, but, I'm still here, and it was cool. I'm glad that I was able to share this meaning of the word conservative. To my knowledge, it doesn't have anything to do with any of the other uses of conservative in math. Like, I don't think it's related to conservative vector field in any obvious way or anything like that. It's just, just another use of the word conservative. I guess because it conserves the elements that are plugged into it. I don't know. It's a story that falsifies Maslow's hierarchy. Yeah, that's right. I was able to eat on a very regular basis, but I did not have adequate shelter, and it was unreliable. I had an apartment back in this is the thing, I had an apartment back in New York, but this was the only vacation the only true vacation I've still ever taken, as an adult. This is the only one after I finished my bachelor's degree. And so I ended up getting stuck there through a series of events I won't repeat right now. And I was like, I have enough money that I can live, and I already have my plane ticket back home. So if I can make it back to the airport at the end of my allotted time, then I can still have a vacation. And being stuck in this beautiful park is not exactly the worst place to be. And so I just went with it, and I did some math, and I hung out at the beach, and that was the only vacation that I took. It was the last vacation that I took too, which was 7 years ago. And so sometime within the next few years, I hope to take another real vacation again. I am living in Colorado now, though, and so that is much more similar to the environment that I lived in when I was living outside. And so it's quite beautiful here as well. And so there's not as much of a motivation to go find nature far away, because if I just go a little bit outside of the city, then I'll have it here. I'll continue to produce math even under relatively harsh conditions. This is another open secret. A lot of people who do this stuff will do it even if we're not being paid very well, because we like doing it. We're kind of like artists in that way. So that was pretty fun. Let's see. I think I've actually managed to answer all the questions at this point without having another question arise. Let's see. We're at the halfway point, just about. Okay. All right. I'll tell the slightly edgy joke that we have about this, in case you're not familiar. Since I saw that there was a comment about universities are going to cite this as a reason to slash the math department funding. So, look, I don't actually feel this way about whatever joke I'm about to make. I don't feel this way about the philosophy department. Like, the chair of my PhD thesis committee was a philosopher. Like, it's not, you know, I don't really agree with the sentiment of this necessarily. But, so people will say, you know, university administrators, you know, really love the math department because, you know, the math department only needs pens, paper, and waste paper baskets, you know, no big expensive machines to be running. But they like the philosophy department even better because they only need the pen and the paper. And so, you know, I don't necessarily agree with the sentiment of that, but that's the joke that people make. So yeah, I mean, we're about as cheap as we can get already. You know, and of course, you know, I'm from the university, or I'm from in the sense that I did my undergrad and PhD at the University of Rochester, and back in the 90s, the administration tried to just gut the department and stop, you know, research or PhDs and just have like adjuncts or engineering faculty teach all the calculus courses. And there was like a big, you know, outlash because of course, like, you can't be a respectable research institution without doing math, right? Like, that's just not reasonable. It's just a basic form of research support for all of the other disciplines as well. And you know, you're going to find mathematicians pretty much all over the place. So not having it is a really you know, was you know, considered to be quite shameful, and they did in fact back down. But yeah, people get this idea every once in a while, like, oh, what are we paying these people so much for? They don't even, you know, they don't even play with the big expensive lasers or anything. What could they possibly be doing? But yeah. Okay, so there's a problem related to. Okay, wait, I'm sorry. What is this? So I see there's a problem related to something that I was talking about, but due to the timing, I'm now not sure what it was. So there's the sequence 1, 6, and then there's a next term that's over 7 million, but no idea what the actual value is. Oh, okay, this is about counting some type of algebraic structure, because algebraic structures are the things that give you sequences like this all the time. Yeah, I mean, you know, do you know about the online encyclopedia of integer conservative? Is it a class of conservative magmas, conservative and associative, or is it just conservative? And of course, the online encyclopedia of integer sequences is a really great. It's a really great place to check for any sequences that you're curious about. Of course, if they have them. So it's a really good encyclopedia. But yeah, actually, there's another really good paper. While I'm thinking of it, there's another really amusing paper that I will see if I can produce for you now. So somebody actually counted the numbers of isomorphism classes of various kinds of algebraic structes just using Burnside's lemma, and it was very nice. It's a bit of an older thing. Okay, now I'm not sure if I'm going to actually be able to find it right away. Maybe I'll post this in the YouTube description. Yeah, there's a really great paper. Cannot remember right off the top of my head who wrote it, but it was from the 60s, and it was like the number of isomorphism classes of algebraic structures, and it was just full of sequences that were like this sequence, and it was all Burnside's lemma. It was really neat. I found that when I was an undergrad, and I was like, this is so cool. I see. It's a few steps removed from just saying like conservative, associative, or something like that. Okay. Well, yeah, 1/6. I'll agree with you that 1/6 is not a very specific search term. You need more than two things in your sequence. Have you tried to actually use some software to just enumerate the possibilities somehow to see if you can just get the third number in the sequence? Because that's definitely a way that you could go. But yeah, if not, or if that just seems too hard, definitely I would say that when doing a lot of these things, it doesn't always work because sometimes these problems are just too hard. But Burnside's lemma is really your friend with these. So using this to count something in two different ways is really helpful for a lot of these things. But yeah, it's or I guess you can say Burnside's lemma is kind of counting something in two different ways. Oh yeah, sometimes the programs run forever. So there's this question about these things called finite projective planes. I don't know if anyone's ever heard of these, but it's kind of like the Fano plane that shows up with the actonions sometimes. There's this question about which sizes finite projective planes can have, and so it's like something that in principle you could just check all the possibilities and see, whether this particular size is possible. The problem is the possibilities are like 100 trillion, whatever, right? Like who knows? It's something really big. And so I remember that there was a lattice theorist at the University of Hawaii who had, JB Nation, if you're familiar, who had, at least last I knew, and this was years ago that I last had heard the progress of this, he had like a dozen computers running for like 10 years or 20 years or something like unbelievably long, running just to see if they could find an example. Because as soon as you find an example, then you're done. You don't have to check all like 12 million it's more than 12 million. It's like trillions. Like you don't have to check all the possibilities. You just have to keep trying things until you get one, if you do. And so I don't know if it was how fancy the setup was. Of course, if you have some really nice supercomputer, you have some like Amazon, web services, or I guess who was really taking over? But it wasn't. It was IBM last I heard. I think, right? IBM is the big thing now, or is it still? Anyway, if you have some supercomputing cluster, then you can really go to town on some of these things. But even with those tools, it's sometimes just unattainable. Like you have to actually understand the problem. You can't just use brute force. Not to mention, it's not very environmentally friendly either to use such a huge amount of power on something that you could really just try to think a little bit more carefully about and know the solution. It's kind of a wasteful thing to do. But people do it from time to time. I mean, I think JB Nation probably wasn't using that much. I think he just had some desktop computers going in a room somewhere in the university. But definitely try to use algebra before using supercomputers. It's the responsible thing to do. So I'm glad that I'm giving people things to read. That's really cool. I definitely want to try to remember to post the reference to this paper, because like I know I have like a library of papers on my computer, and I know I can find it. You know what? I'm just gonna find it now if it'll open up for me here. Let's see. So I'm just gonna find it really quickly now and try to see if I can see where it is in my library. I have a bunch of algebra books, and so let's see. Universal algebra, finite algebras. It's the number of isomorphism types of finite algebras. Here, I'll bring it over here. All right, this was really quite something. Tabby, it's okay, buddy. Tabby, come here. Come here. It's just another dog, buddy. It's okay. Come here. He has to protect the apartment. It's okay, buddy. All right. Oh yeah. So anyway, this is the number of isomorphism types of finite algebras. It's by Michael Harrison. I actually don't know what happened to him. I don't really think he had an academic career in the long term, but I don't remember specifically. Debbie, come here. Debbie, hey, no borking. You can't be borking at them. Yeah, shake it up. Shake it up. Yeah, that's a good little guy. Yeah, you did it. Aw. You want to say hi to everybody, bud? Here, let's see. Let's see if we can say hi to everyone. All right. Oh no, he's too shy. He's done. All right. Anyway, Michael Harrison wrote this paper. Dog tags. Yeah, Michael Harrison wrote this paper, and so what he did here. Let me just scroll through to the actual result. So he's saying he's using Burnside's lemma basically, which is something that you would see in like a maybe a first graduate abstract algebra course, yeah, I found this to be really nice because let's see if we can find the actual result here. Yeah, so he finds like exact formulas for like the number of binary operations on a set up to isomorphism. So like if you don't do it up to the relabeling of the different elements that you have, it's not really very interesting. But if you have to count how many like essentially different ones there are that like look different from each other in the way that algebras can look different from each other, it's much more interesting, and you get some pretty surprising sequences that you can actually find a formula for. Let's see. He does the same thing for an algebra with a higher arity operation, so like like an n-ary magma. He does similar things for other classes of algebras, but he doesn't have any like axioms. So he doesn't include like associativity or anything, which makes it way harder. So like if you have a counting problem like that involves like associativity or commutativity, well maybe commutativity isn't that interesting, but assuming these properties makes it significantly harder to perform these counts. You can already see the formulas are getting a little bit fancy, but yeah, I was a big fan of this paper, and I think he has some of those. Oh yeah, here's the sequences. All right, so these are the number of like fundamentally different algebras just with a single binary operation, like magmas. It goes 1, 10, 3,330, and then 178,981,952. So if you want to mess with people, you can say, what sequence goes 1, then 10, then 3,330, and you can see if they're able to come up with the next number, which almost certainly they will not come up with the answer 178,981,952, because that's just not reasonable. But that's what it is. So that's the number of different isomorphism types, like fundamentally different types of algebraic structures that have 4 elements in a single binary operation, which sounds like really huge already. And of course, if you have 2 binary operations, the numbers get big faster. So even when you have 3 elements, there are already 64,573,605 fundamentally different ways that you can have 2 binary operations on a set with 3 things in it. And so the absolute diversity of algebraic structures that are small enough that they only have 3 or 4 elements is unbelievable. It's really a lot. So I always thought that was really cool. But yeah, that's Harrison's paper from 1966. I see. So I see that there's a problem about colorings of the corners of a 6D hypercube, and that's it's kind of a it's kind of a thing. This is why having algebra, I think, is very helpful, because if you want to think about the vertices of a six-dimensional cube, you can think about the cubes as being like, here's 0 dimensions, here's 1 dimension, here's 2 dimensions, and you keep doubling it, and there's 2 dimensions, and 3 dimensions is like this, and then I'm starting to get a little bit messier, and then 4 dimensions is like you take 2 of these, and then you've got this other one over here, and you've got to connect them together, and so like this has to go to this, and this has to go to this, and it's too hard to draw, and then I can't draw that very good, and so it's kind of hard to picture that, so I think it's easier to think about these as this is like an empty list. This is like a list with 0 and a list with 1. This is like lists that have 2 things in them, 0, 0, 0, 1, 1, 0, 1, 1. And then here you have lists with 3 things in them and lists with 4 things in them, like 0, 0, 0, 0. And you probably already know this, but I mean, maybe you don't. I don't know. You probably do. I would think. But I guess my point here is just thinking about coloring, thinking about coloring the lists, the sequences of zeros and ones is probably a lot easier psychologically than thinking about the actual object itself. You might already kind of know that there's this correspondence, or that you can set up the vertices of a 6-dimensional hypercube as all the sequences that are sequences of 6 zeros and ones. But I think thinking about what a little piece of the hypercube looks like in terms of this, the sequence that's 1 and then 5 zeros, is next to the one that's all zeros, and it's next to the one that is also 1, 0, 0, 1, 0, 0, but that these two are not next to each other, that's not a connection. Thinking about it that way is actually, I think, a lot easier than trying to visualize the object, especially when you're doing something that's labeling all of the vertices. I think that that's probably a lot easier. I mean, that's just my inclination. Maybe that advice or whatever isn't helpful, but I think that that's a lot easier, and that's part of the reason that being able, that doing the sort of algebraic presentation of things is a lot nicer. Because it gets hard to picture the higher dimensional things directly. There's another question though. Scientists wonder why reality is so detailed. Do mathematicians wonder why math is so big? Well, I would say that. I guess the question is what do you mean by big? Because certainly we can describe things that are of an unlimited size. We can even talk about things that are infinite or different sizes of infinity. But I guess maybe that's not the kind of big that maybe that's not the kind of big that we should really be asking about, though, because if I don't know, you might say, and please clarify if you have a clarification to your question, but you might say, well, okay, it's true that you can think of numbers that are really, really big. Here's 1,000. Maybe here's 2 to the 2 to the 2 to the 2 to the 2 or whatever, right? You might say, well, okay, the numbers get really big, but that's not really mathematics in general. Math is all of these different kinds of structures that we can study, shapes, different kinds of algebraic structures, different kinds of patterns that these things have as far as their relationships with each other. And so the question might be more why is this not all somehow reducible to a couple simple principles that just repeat over and over again? And we all try in various ways to simplify things down as much as possible, especially in ways that are appealing to things that we already know how to do, like arithmetic. but it does seem that there's a sort of irreducible amount of complexity going on here. And I mean, I'm sure that there are lots of different philosophies that mathematicians have about this, but I guess for me it's just that there's no like good reason that nature, whether it's like nature in the actual world or in mathematical nature, has to be like simple or understandable to us. Like maybe a good example of this is that for those of you who have taken calculus, like there's a lot of integrals that you can't get a closed form solution to. Like if I just choose, I really am not giving this as a specific example of one that can't be done, although if I just choose a random one, my understanding at least is that if I just say like, I don't know, whatever. If I just choose a random integral, definite, indefinite, whatever it is, like if I just choose a random integral, I'm not going to be able to find an antiderivative. I'm not going to be able to find a closed form expression for the quantity. Now I can't 100% guarantee for you that this is the case for this one that I just wrote down, but it's from what I understand at least, I don't have a reference for this one, but I believe I've heard that this is true from some kind of source, that if you just choose a random expression like this, the probability is one that, like, it's 100% sure that you will have not chosen one that can be done using any method that you've ever seen, or even any method that could ever be devised, in the sense that there's not going to be a nice formula for what the antiderivative of this is, or for what the value of this definite integral is. It's just not going to happen. So in other words, the examples that we know that are nice are like infinitesimally small compared to the examples that are not nice, that are undoable for us in terms of the things that we know how to do, or maybe could ever know how to do in some sense. And so this is just kind of the situation all over the place. When you start looking, you'll discover that there are all of these little bits of provable impossibility that exist everywhere. And so there's always like this little island of things that we can actually compute, or things that we can actually do. And then there's like this huge kind of abyss of things that are unattainable to us. And somewhere in between there are some interesting results where it wasn't clear whether you could or could not do the calculation or understand the thing, but it turned out that we were able to, and that's very nice. But yeah, we have a lot of results like this at this point that there are things that we just are never going to be able to do in any way that we would find nice. And as far as why that should be the case, yeah, I guess it's just that nature shouldn't necessarily. There's no reason that nature should be nice to us. I mean, it's just like saying to yourself, like, well, like why should how do I want to say this? It's like there's no reason that the formulas involved in describing like electricity or magnetism should even be comprehensible to us. Like, we're just kind of lucky in some sense that the structure of our world seems to be amenable enough to this that we can do any of the science that we do. It could have just been the case, I mean, like in principle, right, that the physical laws governing the universe are just different every couple of centimeters, and that there are no large-scale patterns that are predictable enough for us to be able to describe mathematically. And it just happens that somehow those things happen to mesh together well enough that intelligent life can exist, and it just suffers through the confusion of not understanding what is happening around it, but it is able to exist and continue to live. We're very fortunate not to live in such a universe, and yeah, I don't really have a philosophical reason of. I mean, I guess what I'm saying is philosophically that horrifying situation I just described should actually be more likely. Like the fact that nature is even amenable to any of this at all. This is like that, what's like the unreasonable effectiveness of mathematics. Like, we have all of these results, we have all of these arguments that say, like, if you just chose some random rules, you're not really going to be able to understand them probably. And so the fact that we can understand nature at all is actually kind of weird. Oh yeah, so much for getting actual work done today. Well, people ask me to philosophize, so I'll philosophize. I do have a little bit more of my project in working memory now than I did before. Yeah, I don't know. I don't know if that's a satisfactory answer, but that's an answer, is that we see that this kind of bigness in the sense of having just a lot of parts that are not, even remotely reducible to other parts, just seems like it's kind of the name of the game. Like, that's the normal state of affairs. Nature doesn't owe us anything. It doesn't have any kind of obligation to be explainable in any way that we really care to. Okay. Now that I've said that, I actually am kind of inclined to mention another result which would contradict this thing that I just said, this philosophical thing completely. So now I'll tell you a reason why we should expect that we can actually understand just about anything that comes up, even though I just gave you some examples of reasons why maybe we shouldn't expect to be able to understand anything. And these things coexist together, and they're all true things. That's just the nature of reality. I'm just the messenger here. I don't, I'm not responsible for all of this. So math is unreasonably effective, but here's, unless anyone has anything else that they'd like to hear about, in which case just maybe, just mention it in the chat. I'll say why we should expect that we can understand anything in nature, for mathematical reasons that are also related to abstract algebra. So it's still the same kind of stuff as I was talking about before. All right. So what's the reason why we should be able to understand everything? Well, there's a theorem that I've mentioned in some of my YouTube videos before. It was part of the reason that I started doing some of the artificial intelligence work that I am still doing now. It's called Mirsky's theorem. I think the second I has an accent. And it's from the 70s. And Mirsky's theorem basically says, choose a big random set, just A. Okay, so I guess maybe I shouldn't say random. I guess here. Okay, I'll say this in a less evil way, so you're not worried about what a random set is supposed to be. So just choose a big finite set A. Like maybe it has like 100 billion elements in it or something. Oh, I see. I've activated the simulation theory stuff here. Yeah, if it was some kind of simulation and a big alien supercomputer, it would have reliable rules because that would make it easier to do the simulation. It's an interesting thing to think about, and it's kind of related to like the anthropic principle of like, well, it's so unlikely that we exist. Why should we exist? But we wouldn't be here to talk about it if we didn't exist. Maybe a random set of rules would be harsh to us, and we exist in a nice set of rules because that's what would support intelligent life. That's an idea. But here I'm actually going to use abstract algebra and some probability to explain why any random set of rules should be able to give us some laws of physics that we should be able to exist in, which is probably kind of surprising. So choose a really big finite set A. Choose a couple randomly, just a couple randomly selected operations on A, by which I mean like maybe you maybe you have a rule that is, maybe I'll call F. It takes triples of things from A to other things in A. Maybe you have another one called G that takes, maybe you can feed it 17 different things from A, and it gives you back a thing from A. Okay? Well, just choose some random operations like that. Just randomly chosen, their values or whatever. They don't have to have any nice properties, just like literally whatever. Just as long as they're functions of that type. If you choose a big finite set, like it has like 1 billion elements, 100 billion elements, and you choose, that's supposed to say a couple. I think maybe there's a U in there somewhere, who knows. You choose a couple operations like this, maybe like this F and G. There is a like 99.999 or so approximately % chance, if I could spell chance correctly maybe, there's like a really, really high chance that any operation, so any other operation, H, you can have whatever number of inputs too, like 6, whatever. Any operation that you choose like that is a composite of your randomly chosen operations like F and G. Okay, so that's basically what Mirsky's theorem says. Choose a big enough set of basic things, like your elements for your physics, if you want to think of it that way, maybe your subatomic particles or whatever, and then choose like some random operations, like just whatever, whatever arities you want. Just choose a couple of them. They're defined, however. Just choose your basic rules of physics arbitrarily. There is basically a 100% chance that those rules of physics will actually allow you to describe any particular kind of reaction, if you want, like any kind of rules that you would like to in terms of those. That's kind of a down-to-earth explanation of what this result says. But what that means is that the universe didn't need to be chosen in a careful way. You could have actually chosen deep down at some subatomic particles that we can't even fathom at the moment, that the rules are actually completely arbitrary. It just happens that you can describe any kind of nice regular structure, like the structure that we exhibit, in terms of those very unpleasant and nonsense rules. You're basically guaranteed to get that. So even if our universe was just randomly selected, the basic rules for our particular thing were just randomly selected, it would be possible for structure as detailed as us to exist within it. In fact, it's basically guaranteed that it is possible for such structure to exist. And so this is just a purely mathematical thing. I didn't really use anything from physics as we understand it about the real world. But if you believe that the universe should have some kind of mathematical description like this, it's actually guaranteed that even just complete nonsense rules that have no particular structure whatsoever can give rise to all forms of structure. And that's pretty surprising. It's a really shocking thing that should be the case. But yeah, you can prove it. It's a theorem. Let's see. Yeah, it's not surprising that we develop theories that are useful in describing the world, in the sense that we're just making the most sense of it as we can. And yeah, I mean, I agree that, of course our theories make sense to us because we're the ones that came up with them, and we see that they don't always agree with the world, but we just try to find the best ones that we can. Oh yeah, I can type the name into the chat. It's I don't know if it has a Wikipedia page, but it's Mirsky's theorem. So there's actually a book here. Let me see if I'll send you a link to a book that has this theorem described in it. Because I can just send you the actual the actual website for the textbook that I found this in. So So yeah, that book has it has a proof of this theorem in it. It's towards the end of the book, and so I really kind of I did it justice, but I did definitely simplify it a bit. But yeah, this is one way of thinking about Mirsky's theorem. And this really isn't that much of a simplification either. Like, this is basically literally what it says. I guess I'm just being a little bit, I don't know, being a little bit humble or something, or trying to make it. It's not really that much more than what I just described. The hard part is just actually proving that this is true. So for anyone who knows like more about combinatorics, you need in order to prove this result, you need like the sharp form of Stirling's approximation. It's a pretty touchy combinatorial thing. It's not easy to prove the limit, like to show the limits that you need to show for this, but it is possible. Oh yeah, great! After finishing Dummett and Foote in 2030, so it'll be time to start universal algebra. I actually kind of learned universal algebra along with like classical abstract algebra, in the sense that this is like naturally what I was kind of interested in, and you can see that a lot of the intro universal algebra, especially like in the book I just linked, it feels very similar to like intro group theory or ring theory, and although it does maybe take some more mathematical maturity, it is actually very close as far as like the how you prove the results. It's just kind of everything with a bunch of just higher arity operations as opposed to what you did in group theory or ring theory. But a lot of the first stuff feels very similar. And so it is possible to learn universal algebra to some extent without going all the way through Dummett and Foote. But it is good to have as much algebra experience as possible, because it's just like learning category theory, where it's an abstraction, and so if you don't have as many examples going into it, it's a lot harder to understand why anything's happening or get intuition for it, because you need the examples to know what these things are really talking about. Otherwise, it's just abstract nonsense. Although the nice thing about universal algebra too is it is more down to earth in that sense, and it's a little more concrete than category theory, in my opinion. But yeah. So yeah, I'm glad I was able to actually find those references and share them. Oh, and I guess I should tell a story too. So the from Dummett and Foote, I think his son was a postdoc at the University of Rochester when I was an undergrad, and he taught my undergrad dynamics course. That's what it was, and it was a cool course, and it was a good time. I actually talked to him about my interest in universal algebra, and we had a good long conversation one time, and it was really nice. And he was like, even though it's not something that I do or not something that I'm interested in, it was cool to talk to you about it for a while. And I guess I always remembered that, because like it's just I don't know, when you're an undergrad and like you're just you're getting interested in different things, it's cool for professors, postdocs, tenured people, whatever. It's cool for professors to actually just take the time to kind of hear you out about your interests, try to see if they can point you in the right direction. It always means a lot. It's something that people really remember. Yeah. But okay. One other story about the younger Dummett. So I think he maybe not literally always, but he very frequently wore like gym shorts and like tie-dye t-shirts to every class. I'm glad that you appreciate me hearing you out. It's cool. It's cool to hear from so many people and give some feedback and stuff. But yeah, this guy, not the guy who wrote the book, but his, I think it was his son. I don't think it was his grandson. I think it was his son, but I'm not sure. he just always wore this outfit basically, and he was a postdoc. You know, he wasn't tenured or whatever, so he wasn't like, you know, having some kind of tea with the dean every day or something, I guess, you know, or whatever it is that people wear suits for. But I always remembered that, and like it, you know, it's really interesting what's going on with what outfits people wear in academia at the moment, because math gets a little bit of the computer science, like jeans and a hoodie. You know, you're going to be the next Silicon Valley, you know, coder person. You don't have time to, you know, have your pocket protector and your button-up shirt and all that, you know. But I think as a woman, it's even more interesting because you also have the, you know, the kind of dynamics that go on around gender in the workplace and everything. And I always felt like I was kind of immune from anyone saying anything about what I wore, because that would be like, you know, they would just burst into flames because of the political implications. You know, I was informed at some point that I should actually like wear like slacks and a suit to like go to, or you know, not a suit, but like, you know, like a pantsuit or like some type of like blazers. Like I should wear blazers to like go to like job interviews. And so I went and I bought all these clothes, you know, and I was like, okay, I'm gonna, you know, be like more like old-fashioned or whatever you're supposed to do in order to get a job. And then I ended up getting this job at CU Boulder, and I had already given a talk there recently before getting all these clothes and everything, and so on the basis of that talk and visiting and, you know, everything, they hired me. And when I went to that talk, I just dressed like I always do. I don't know. I just wore like shorts and like, you know, maybe I had like a collared shirt that I had unbuttoned over a tank top like I always do. But I just dressed the way I always do, and it was fine. And like, so like I'm now going to be applying to tenure track jobs at the next stage, and I like have no idea what's really like what's required or what's like gonna, you know. And it's like, there's no way to really know, right? Like, I can ask individual people, but, like, the bottom line is, like, people are primed by what you're wearing. People who are more conservative won't tell you that they're judging you if you don't wear the clothes that they think that you should wear. And, like, it's just, like, unknowable. And so I have no idea what I'm actually going to wear, like, when I have a tenure track job interview. I just have not the slightest clue. So anyway, that's my dissertation on my outfits. Yeah, that's that's what it is. I think my audience tends to skew intensely male. I don't know what people's genders are here, but you can just ask me if you're really curious about that anymore. But I imagine that it's maybe foreign to a lot of people. I know my YouTube is like almost 100% people who have their gender as male watching it, from what YouTube's data analytics tell me. But yeah, in case anyone is curious or anyone's watching on YouTube at a later date, you know, I'm happy to answer questions about that too. But as you can see, I'm still a bit confused myself about the clothing situation. I do like wearing blazers. I do find it to be fun. It's the slacks that are really getting me at the moment. I think I just I'm not sure about that. It just makes me feel like I don't know, like an office person from like the 1960s or something, or like it makes me feel old. I'm not really sure why. But okay, that's enough of me. It's enough of me ranting about that, I suppose. Are there any other mathematical things that people are curious about, or if not, maybe I'll just see if I can actually figure out what the calculation was that I was doing earlier. And in case you're not super crazy about that, I'll also be doing something totally different next week, and I'll just keep doing a different thing every Monday evening for every week for the foreseeable future. You know, I'll just keep doing different stuff, and just I have basically an unlimited amount of different random things like this that I can talk about, or that I've been thinking about working on. I literally find old papers that I wrote when I was an undergrad or a grad student, and it's like a whole paper. Like, it's like an entire paper with like references, it's all teched out and everything, and I'm like, when did I write this? Like, it's not like I literally don't know. Like, I can usually remember having the idea, but I just forget about some of these things for so long. I'm like, I should post this somewhere. And I'm like, I'll do it later. It's too much work. I'm going to show you guys those things. Because what else am I going to do with them? It'll take me forever to actually post all of it. Yeah, so I'll do something that's a random thing I wrote 10 years ago or something next time. Maybe try to clean it up and see if I can actually post it online finally. Alright, well, yeah, if there's not anything else that people are curious about at the moment, let me see if I can figure out what was going on with this paper that I was editing a while ago. Oh wow, we really got into it here. I see. So maybe one other like side thing, just to explain like a little bit better what I was doing here when I was doing this, like way at the beginning. Oh yeah, I have some I also have some coding projects that are like this as well that I can pull out. That like I'm like, oh, I made this one time and then I never posted it on GitHub. Like, you know, yeah, that's where I have a lot of like my like fractal art and like different kinds of like things. Like you can see like my icon down here, you know, for like my profile on here is like some kind of like some cellular automaton type thing that I made, and I haven't posted the code online still, even though it's been like 8 years. Yeah, there's a lot of stuff like that going on. I actually rewrote that code recently, and it's way nicer now than when I was younger. Like I feel so much better about it. But yeah, I guess here's the thing to mention. What I was trying to do before was something to do with manifolds and charts and stuff, and I guess if people are interested, I'll remind you of what's going on with that. So, just about manifolds and charts and stuff in general. So, a manifold is something that's like, for the 2D case, it's something that's like a sphere, like a beach ball, or it's something that's like a donut, like, you know, like an inner tube kind of thing. Or more generally, it's like a donut with many, many holes. And that's what a two-dimensional manifold looks like. And so, being a little bit more formal, a manifold is a topological space. And so, if you don't know what a topological space is, the rest of this might get a little bit more vague or abstract. But a manifold is a topological space where if you look at any point on it, that point has some little neighborhood, like some little circle around it, that looks like Euclidean space. Or in other words, that looks like the plane. Like you can think about there being a little piece of this thing that just looks kind of like a circle. And that dot's supposed to be like the middle dot here on the donut. And you can do that for every point on the object. So like every single piece of this object has some little neighborhood where close by, it just looks like a little circle. Now, of course, the whole big thing might not be just a circle or just a flat plane. It might be something more complicated. But at least close up, everything just kind of looks like a little bit of 2D space. And that's what makes this a two-dimensional manifold. Or all of these things I drew are two-dimensional manifolds. And as you can see, they can have different structure. The ball and the donut aren't really the same shape, but they're both 2D manifolds. So now there's actually about like a bajillion different kinds of manifolds, and so if I'm being a little bit more careful, what I just told you was what it means to be a topological manifold. Okay, there's like one other part of the definition too, but I think that part of the definition is evil, and I'm not even going to mention it, so it's fine. Two-dimensional manifold, it's a thing where if you zoom in, like close up, little pieces of it look like 2D space. Let's just leave it at that. That's pretty much what a two-dimensional topological manifold is. So now the thing that I was talking about with the charts is that some people say like this definition is too loose. Like Oh no. Okay, I don't like the line with two origins. If you know about non-Hausdorff manifolds like the line with two origins, I don't want to do that. I just wasn't mentioning it for people who didn't know to not. Oh my god. Okay. All right. All right. Look. I will mention this evil briefly, but let's just try to steel ourselves against it, and I won't continue with it when I talk about charts and stuff because it's not allowed. All right, so over here, like okay, maybe over down here this will be the bad non-Hausdorff zone over here. Okay, okay, so. This is going to be the bad area over here where bad manifolds live, and so you could imagine. All right, so these are two-dimensional manifolds up here. You could imagine there's also a land of one-dimensional manifolds, and the one-dimensional manifolds, every little piece of them looks like a little piece of the line. So like here, maybe there's a little piece of this circle. Little piece of the circle looks like a little piece of the one-dimensional line. Looks like a little segment. But the whole thing isn't a line, it's a circle. And if you think about it, there's not really very many one-dimensional manifolds that you can come up with. And also here there are other things that are evil for different reasons, like the long line, that we're not going to worry about right now because we already have one bad zone and we don't want to introduce a different one. Well, okay, the uncountable disjoint union of lines I actually don't have much of a problem with. So that one I don't consider to be too evil. I'm talking about like the long line, which is longer than the regular infinitely long line. But yeah, let's not get into that. Okay, so if you really want to know like my true beliefs about this, and you can see this in even the preprint that I was originally talking about that's on the archive. What I think is what I think is right and proper for manifolds is that they're allowed to consist of an uncountable number of connected components, but each one of the connected components has to be second countable. I think that's the proper way for it to be. I think that's just what makes me happy, and so and they do have to be Hausdorff, like that's yeah. Okay, but yeah. Anyway, yeah. Thanks for the approval. I need to get emojis going on here. I need to have like manifold emojis or something that like comes up when like things happen and. Can be like, can I get a smooth manifold in chat? And like people will be like, like the donut or like the sphere or whatever. I will learn to use this software and try to make that happen. So that'll be good. For now, you can just write smooth manifold if you would like, or maybe some other notation if you're familiar with. Yeah. We need the yeah. Yeah, and then we need to get artsy with it. Maybe my partner can help, and we can get like the many-hole donut with like sprinkles on it or whatever, and like have like all the different like little like decorations to make it look edible. It could be pretty cool. Oh yeah, but okay, the bad non-Hausdorff land over here has the following one-dimensional manifold. If you look at the folds in our brains, it does kind of look like it's a smooth manifold, but yeah, yeah. So the line with two origins is like you have like the real line, like you have like the usual number line that goes on in both directions. But where the number 0 would be, there's two different versions of 0. There's like, I don't know, 0, or, I guess I did prime. Let's not call them 0, that's confusing. I'm going to call them A and B. Or no, I'm going to call them alpha and beta because I decided to be Greek for some reason. So you have all your usual numbers like 1 and pi and, negative, square root of 3 and all of that. But then where you would have 0 you just have a hole that's missing, and you have two things, which are alpha and beta. And if you look close up to alpha, like if you look just right by alpha, alpha has all of the stuff over here next to it. Like it has all of the stuff over here right next to it. All of the numbers just above 0 and just below 0. Beta also has all of those things right next to it, but alpha and beta are not next to each other. Or if I'm being more formal, there's no open set, or there's, you know, or what am I trying to say? There's open sets that contain like all of these numbers right here, and alpha or beta, but they don't have to contain the other one. So these things are separated from each other in a topological sense. Like, you can't separate them by finding like two totally separate open sets where one contains alpha and one contains beta, but you can find open sets that are, you know, contain one but not the other one. And so this is definitely not a Hausdorff space. And each of these points is like competing very hard to be like 0, but alpha and beta are different points. And so it's like when you approach 0 from either side, there's like kind of a portal, and you have two choices. You can either go to alpha or you can go to beta. And if you go through one of them, you can come out to the other side, but you never went through, like if you go through the alpha way of going, the alpha portal, you just get to the other side into the negative numbers, but you never see beta. You just don't see beta. It's invisible to you. And similarly, you can go back through and go through beta. You'll never see alpha or whatever. You can choose to go through either one each time. And this is the line with two origins. That's what was mentioned before. It's the line with two origins. And so this is in the bad now non-Hausdorff manifold land. And so we generally don't speak of such things. Okay, just pretend that says line with two origins. Yeah, actually, the field... Okay, so I can give a rigorous explanation of why the field of topology is evil, actually. Because in a categorical sense, evil means to define things by equality instead of isomorphism. And so homotopy theory is, you know, not evil by this definition, but topology is, in general, you know, pretty evil. And so, you know, the homotopy theorists are really concerned with not being evil, and they go off and they have their infinity categories, and they're really concerned with, like, you know, making sure that everything is compatible up to all of these higher levels of compatibility, so they never have to say that anything is actually the same as anything else. Okay, wait, why is homotopy equivalence less evil than homeomorphism? So, I mean, okay, I guess I was being flippant, but let me I guess explain a little bit more carefully, since we're going down this rabbit hole. Yeah, so the meaning of evil. So the meaning of evil is like to say that for instance, like a meaning of evil is to say the product of two sets, you know, A and B, is the set which I'll write as A cross B, and I'll define it to be the set of all pairs where A is in A and B is in B. So this is evil because this isn't defined up to isomorphism in this isn't. Oh, sorry. Okay, I'll have to make a less than three emoji. Yeah. So this is evil because this isn't really defined up to isomorphism. Like a better definition would be to say that a product, like not the, but a product is something that makes a certain that is a certain like universal solution to a certain kind kind of problem of, it should be something that has maps like this that are the projections that say, this is the one that chooses the first coordinate and this is the one that chooses the second, and like if you've seen category theory, you know where this is going. But like this kind of definition where it's a product and it's not just given by a formula like this, but it's actually just a general kind of condition that something can satisfy. That's what it means to not be evil. And so saying that homotopy equivalence is like less evil than homeomorphism is I guess is like because the thing is like people, I guess I wasn't talking about like the homotopy category versus like the usual category of topological spaces. I was more talking about like how like people who do homotopy theory like to actually put homotopies in their notion of like what a category is, like that they want that to be like they want everything to just be up to an equivalence and not like up to like not up to an isomorphism even, or okay, I guess this is how I can say it, is that isomorphism is evil. Okay, yeah, this is why. Okay, isomorphism is evil. If I was really a homotopy theorist, then I would have come up with this immediately, because an isomorphism between A and B, right? It's a pair of morphisms like this and this, so that if you do F and then G, you get the same thing as the identity for A, and if you do G and then F, you get the same thing as the identity for B, and this equal sign is the evil thing that is occurring. And so even homotopy equivalence of spaces in this sense is not enough if you were really gonna do it up more seriously, like homotopy theoretically. You would really want that there's some kind of equivalence between G of F and the identity morphism, and that equivalence would be up to some other kind of equivalence, and so on and so forth. The joke is that it's like when Bill Clinton was being interviewed about the Lewinsky affair, and he was like, it depends on what the definition of is. That's what is seen as not being evil in my understanding of homotopy theory. They want that homotopy type equivalence everywhere. Yeah, infinity groupoids and infinity categories and all of that type of stuff. I usually don't mess with it. I may have started poking into two categories a little bit at this point, but I don't have a lot of designs on higher categorical structures at the moment. I have maybe one or two ideas that are related, but I don't expect to hear about anything beyond two-dimensional categories anytime soon for me. Except for when I'm talking nonsense like I am right now. I think I may actually be able to define an infinity category still, but I don't really work with them. I can give you the intuition too, but again, it's just me repeating stories. Oh yeah, I'm glad this makes some kind of sense too. And then there was a question which I didn't get to yet, but which I'm happy to get to now. Is it weird that category theory came out of topology? I mean, I don't really think it's that weird, because do people know the story? Like, do people know where category theory came from? Are we? Oh, defining nonsense is the first step to defining sense. Yes, absolutely. And yeah, you do have to put the space in between the less than and the 3 here if you don't want to get the purple heart emoji. But yeah. Abstract nonsense is a great thing. Maybe I'll just say just very briefly. The people who originally came up with category theory weren't concerned about this notion of what is equality versus equivalence and all of this type of thing. That's not what they were concerned with. They were concerned with the following, and here's my very brief historical story. What were they interested in? Well, you know how I've been talking about taking some kind of algebraic structure, like a group, and then making some kind of manifold out of it, some kind of shape out of it? Well, what the people who were, so this is me and other recent people. So what were people concerned about with back in the 60s or so? So this is like Eilenberg, McLean. What were they concerned about? They were concerned about taking shapes like this and turning them into some kind of algebraic structure, so that they could use. Oh, somebody started doing the zero with. Oh, okay, yeah. You can use zero with spaces if you don't want to put a whole space in the heart. Here, let me move my donut over a little bit here. So what were they concerned with? They were concerned with taking shapes like this and turning them into algebraic structures, like groups. And they wanted to do this because they thought that they would like to understand the shape by understanding the group. And that's what's called algebraic topology. And so, what they were really interested in understanding was this process of constructing these homology or cohomology groups, as they were called, from these spaces. And so it was the case that they were interested in making these algebraic structures out of these shapes, and they had different ways. Of doing it. Maybe there was kind of a one-dimensional version of this. Maybe there was kind of a two-dimensional version of this. Where you could take the donut and look at its two-dimensional homology, and there was one of these for each dimension. And then there was also one of these for each shape. So you could also think about what is the first homology of the sphere instead, like the 2D sphere, or what is the second homology of the 2D sphere, and stuff like that. And if you had some kind of map from the sphere to the donut, there would also be a map in the first homology. Maybe I'll call this H1 of F. And there would also be a map in the second homology. It was H2 of F. And they noticed that sometimes in cases like this, there would be this kind of natural thing that you could do where you could say, well, I can either send the first homology to the second homology, and maybe I'll call it eta sphere, or I could send the first homology to the second homology for the donut. And sometimes I can do that so that if I do H1 of F and then this eta thing, and then or if I do the eta thing and then I do H2 of F, I get the same answer either way. And then they draw a little thing like this. And I don't know for sure exactly how they drew it, but that was the type of thing. This is what a natural transformation is. This is a natural transformation. And so I don't know if this is this exact form as the natural transformations that they were first. I don't know what exactly they first considered, but what they first defined was a natural. They wanted to talk about natural transformations. This was the thing that they cared about. The notion of a category, the notion of universal constructions, and all of that, was just a consequence of trying to formalize this thing. It is a natural transformation between functors. Even functors are auxiliary to the original idea. It's really natural transformations that are what it's about. So now you've heard the story, and I hope that this bears some resemblance to what really happened. This is obviously a third-hand story, since I'm from now and not 30 or 40 or 60 years ago. But I believe that's about what took place. Yeah. So that's how category theory came to be. Was people wondering about these natural transformations. So why was I talking about manifolds? If you remember before, I was trying to explain what was going on with one of the first questions that was asked, actually, or maybe not questions, but one of the first things that someone brought up, which is what's the deal with charts? And so a manifold is one of these things that's made of a bunch of pieces that look like a piece of the plane if it's 2D, a piece of the line if it's 1D, or whatever. And well, what I defined before is a topological manifold. And a lot of people think that topology is not enough, and they want to do geometry. I'm glad that people have enjoyed the stream. If you have to pop off, I will still be here until 9, as promised, for those of you who are sticking around or have joined us more recently. But yeah, thanks so much, everyone, again, for the awesome time so far. And I'll now endeavor to explain what was going on with charts, so I can at least explain a little bit better what I was just trying to do at the beginning. Yeah. So. Right, so we have these charts, but these charts kind of don't really have to have anything in particular to do with each other. Maybe one way of illustrating this is that you could think about, now I have to find more space again, where do I have real estate? So, if I did something like a triangle, I could think about having this whole piece of the triangle is I could think about a chart like that. I could say, that whole piece looks like a line segment. Sure, it has this angry point in it, but that's okay. And then I could say, what about, I could choose this piece over here instead, that sort of piece of the triangle. That also looks like a line segment. And similarly, I could do this with the other part too. And I could cover these things with pieces that look like a line segment, a bent line segment. But depending on how I do this, it might not really be very nice to compare the results on these different line segments. For instance, maybe all of these are ways of sending the interval between 0 and 1 into my triangle. So maybe this is 0 for this line segment. Maybe this is 1/2, and maybe, so that's supposed to say 1/2, if I can try to write 1/2 more clearly. And maybe over here, maybe this is 1. So that's sending the whole interval into my triangle somehow. I could think of a different way of sending the interval onto the triangle, where I cover, say, this piece, and maybe this is 0, and maybe this is 1/2. Why not? And maybe over here at the point, maybe that's 99 over 100, and maybe and then all the way over here, this is 1. So I've kind of jammed the first half of the interval in this little piece at the beginning. So this is totally fine for a topological manifold. I can put any kind of identifications of the line segment with part of this thing as I want to. But this is not good for doing geometry. This is not a reasonable thing to do if I wanted to do geometry on this shape, because by default the triangle as a topological space doesn't have any lengths associated to it, and it looks like on this side that this segment over here, it looks like it has length 1/100. But the same segment over here looks like it has length 1/2. If I want to have any hope of measuring distances on this thing, this is not correct. I can't I can't have two incompatible notions of distance like this, because I won't be able to compute the same distance for the same segment of my shape. I won't have the same length. And that also means like I can't do things like calculus on this shape, because even if I have a function defined on it, because I can't measure the length of a segment of this shape correctly, like there's not a single answer to this. That means that I can't. That means that I can't know. I can't know how to integrate anything. Like I'm not going to be able to consistently define how to compute integrals. None of the stuff that you would like to do with shapes mathematically is going to happen. You need a consistent way of identifying pieces of your shape with pieces of Euclidean space, with familiar space. And so, so the idea is that we think of each of these identifications of saying like, okay, this piece of the triangle is like this line segment, and this piece is like this line segment. We think of these as charts. Like maybe this one's phi 1, I don't know. It goes from the interval from 0 to 1 into the triangle. Just draw a triangle. It's a triangle, it's not the letter delta. Maybe this is like phi 2. It also goes from 0 to 1 into the triangle. And these are examples of charts, like in the theory of manifolds, differential geometry or whatever. And so if you have these that cover every point in your shape, then you have a topological manifold. But we often want to have something that has a nicer structure, so that, for instance, we could maybe try to do something like geometry, and that means that we need to have more than that. And so what we think about is, what if I use this chart to go into my shape, but then I use this chart to come back out? In other words, what if I looked at this? Like I did phi 1 to go into the triangle, but then I did phi 2 to come back out. Well, if you think about it, phi 1 goes from the interval into the triangle, and then phi 2 inverse goes from the triangle back to the interval. So this is a map just from the unit interval back to itself. You might say, well, what's so great about that? I mean, maybe it's true, but what's the big deal? Like, why do I care? And we care because this is just a function from the real numbers to the real numbers, and we can actually do calculus the way that we know how to do it on this thing. All of the geometry and calculus that we know from high school, from whenever you learned all of these things, we can use it on this function. For functions on general topological spaces, we don't really know before this what's going on, but for functions from real numbers to real numbers, that's stuff that we did in calculus. And so now we can start asking things like, the most basic things would be like, is this continuous? Is it differentiable? Is it a smooth function? Does it have an unlimited number of derivatives? And each of these gives us a different kind of manifold. And so in the paper that I was working on, I needed to show that I had a family of charts like this, that whenever you transition from one chart to another, this is like called like a change of coordinates, like a transition map. We want this to always be a smooth function. And so that was my goal, was to show that for the charts that I had defined before, that this was actually going to be a smooth function. And so I know that this is not going to be a very hard thing to prove in my case, because I believe very strongly the pictures that I can see in my head from having worked with these things for a while. But it's going to take a little bit of time to actually write out the details. And I may not be able to do it in the next 17 minutes, but I will continue to poke around at it or discuss whatever questions you have, or hear any comments or anything, until that time. But again, I just want to thank you all so much for checking this out and sticking with me. If you've been hanging out for a lot lot of this. We've had a lot of really cool discussions. Like, I guess it's not that close to being over, but I guess I'll just say, like, I don't know really what I expected. I didn't really have any expectations just because, I don't know, like, this is a totally new thing for me. It's a really new experience. I mean, I've answered different math questions people have had, of course. That's kind of what I do. But, just doing this online, having some crowd of people, I'm sure mostly recruited from Mastodon, although I did some other advertising, interpersonally. Oh, cool. Yeah, I'm glad for someone coming from a different area of math that it was really helpful or interesting. Like that. Yeah, like because that's what we should be doing. I really do believe that math is like a single. It's a single whole. It's a single complete thing, and an absolute unit, if you will, and all of the parts of it are connected. I mean, I even mentioned probability, although I didn't use it. I didn't use it as such very much, but I mentioned probability when I talked about Mirsky's theorem. I also don't know if I'm pronouncing that name correctly, by the way, but you saw it in the chat. As far as my Monday evening productivity, I mean, it's hard to say exactly what I would have done, but I do feel like this has been a really good exercise, and I want to continue doing this. I'm going to have, it won't just be the same paper I'm always working on. I'll just bring up like different random things, either an old paper from undergrad that I'm trying to revamp, maybe finally post, just different things that I'm working on. I may actually do some coding at some point. But yeah, I'm just going to keep doing this every week like this, I think. And if it actually gets going really well and I have some regular attendance, then I might bump it up to 2 times. I'm considering adding another time that's better for Europe. I'm really excited about this. Oh, great! I just had someone come from YouTube that my videos are recommended. I'm glad that the powers that be at Google decided that I wasn't too big of a Google hater to to advertise the videos. I mean, I do have a YouTube channel after all. I'm making them some kind of money, right? But yeah, I'm really glad that you checked it out. It's been really cool. You can also follow me on Mastodon. There's links to my website. You can find my stuff if you want to see more. I'm glad that people are looking forward to more math streams. Yeah, like this isn't meant, as I said at the beginning, this is not meant to be like an academic talk where like I just plow through on whatever thing it is that I'm doing without like, any consideration for who's around or what's going on. Like, my default activity will be to have something to work on, but I'm not just trying to lecture you. I really want to know what you have questions about. I can tell you stories about my life. I think 3 hours is probably a good amount of time, because I do tend to go on a little bit. But that's perfect for this format because people can pop in, hear some stories, just whatever it happens to be. And yeah, I think that this is really a good outlet for some of this for me, because like I have so many things like this. I am always finding new stuff, and I have a lot of like stories or things that like that thing about Mirsky's theorem and like physics. I've said that to people in person like 5 or 6 times, and I always kept thinking, I should make a YouTube video. I should plan out a YouTube video and like give a talk about it and be like, what if the universe was just made of a bunch of particles that were combining according to some completely like randomly chosen rules about how a finite set, has some operations on it, and then say, Mirsky's theorem shows that we could still have all of the physics of our actual world that we live in, and the laws of the universe could just be random and it would still be able to make our universe. And I thought that would be a cool video to make, but it's so much work. Like the psychological effort of like having to like prepare like slides or pictures and like all the stuff, it's exhausting. But I just want to be able to talk to people, whatever their background, like just like I would talk to somebody on the street who for some reason was inclined to listen to this story about, what if the universe was just made up of some random rules on a finite set. That, that's just, yeah, so I'm really glad that I've found this kind of platform, and I'm glad that Twitch, is providing it. You know, I hope any advertising they're doing isn't too intrusive. I have been advertising my own Ko-Fi on the chat, but otherwise I can't see whatever ads. If there's other ads that you can see, I can't see. Please let me know if any of it's ever too intrusive, though, because I appreciate that their servers are being useful to us, but I also don't want to overwhelm you with nonsense. Not that kind of nonsense anyway. So yeah, also feel free to message me on Mastodon, or you can find on my website. You can even just email me with a question. If your question is something about anything that I can reasonably answer, I guess I'll just say I will try to answer your question. I don't anticipate getting an unlimited number of emails, so I will usually be happy to answer whatever question you have. I'm really stoked. I think this has been really cool. I'm hoping. I have not recorded for this long on this system before, so I'm very hopeful that this recording comes out good and that it's okay. And then I'll be uploading it to YouTube right away. Nothing cut. You can watch me, misspell things and the whole 9 yards. Also, I don't know if anyone's into this type of stuff, but if you want to, feel free. You can, just cut out a piece of it if you thought that I explained something well, or you had some story was interesting. You can go and tell Dummett that I was talking about him, or whatever you want. I don't think it was a bad story. It was actually just kind of a fun anecdote. Just feel free to make whatever use of this you want. I've actually never really tried to teach someone else differential geometry as such either. So this is kind of an interesting. Thing that I ended up here with at the end too. I guess I'll also say I know a lot of this maybe feels like messing around or not being as productive or whatever, but this kind of messing around is how I got to know all of these things. There's a lot more of this than there's been reading textbooks. Reading textbooks can be helpful, and doing exercises in textbooks can be helpful, especially at first. But doing this kind of stuff is how I actually understand what I'm working on right now. The complexity of that project is just a result of doing things like this over and over again, and hanging out with different people and having different conversations like this. Also, if I can talk about something a little controversial, I guess too. I think that this is one reason why learning from some kind of automated system, or just learning from people online who you can't interact with in any way whatsoever. I have lecture videos on YouTube. If you check them out, if you have checked them out, I'm glad that that's useful to you. That's a good thing. There's no question. I do listen to lectures on YouTube sometimes. It's just sometimes it's not the main thing that I do. But you've got to talk to people at some point. Math is, it's a community, and it's a living language. It's like trying to learn French by just reading textbooks. And take it from someone who, after all these years, doesn't really speak French very well. You can't do it that way. It's not going to work out. This is really the way to go, is to actually have some kind of use for this stuff, to have some people to talk to. It's very hard to learn how to do math at any reasonable level without that kind of culture and community. And you heard, even, I don't know how many of you this applies to, but I talked a little bit about the clothes that I would wear at interviews, and I've mentioned different things that were sociological as well. And that's an important part of it. It's not the substantive content of the thing, but it's part of the culture around it, you know? It's like how music just isn't about, like, you know, the sheet music notation, or, you know, what constitutes a chord or something like that. I'm not very musical, so I'm not really an expert on the technicalities of music, but you probably see what I mean, right? There are genres of music, there's subcultures, people have, like, style, you know, there's points for style. I mean, that's the same thing in math too. There's different things that become fashionable and then fall out of fashion. There's different subcultures around different kinds of things. If you're familiar with any of these areas at all, you know that there's a difference between people doing, like, you know, harmonic analysis and homotopy type theory. Like that's not to say that you're not allowed to do one or the other if you're a certain type of person, but, like, you know that there are, like, at least some kind of, like, stereotypes, notions of, like, what the difference is between people who do analysis and people who do algebra and, like, this type of thing. And as long as it's within reason, those things can be fun and cute and healthy to just, you know, be like, you know, it's like, you know, the different way that you eat your corn or whatever. But, like, yeah, I mean, it's definitely a community, and we shouldn't stereotype ourselves too much. But, you know, it's a culture, I guess, is what I'm trying to say. Well, I'm really pleased that I've been able to actually rant for 3 hours. I thought I would have to, like, either get up and, you know, take a break or get a drink, but I mean, I do usually, well, if I lecture for 2 hours, it's really me taking a break in the middle for, like, 10 minutes. But, like, I can actually just keep going for a basically unlimited amount of time, it seems. So I will just go right until 9, but, you know, or 9 for me. But yeah, thanks again for checking this out. I think I'll mention that you know, it'll be more interesting. Okay, if I can propagandize you a little bit, it'll be more interesting the more people that there are. So if you want to check it out next week, or even if you can't, but you know want to keep it going, please do let people know that I'm doing this, and that there's probably even more stuff that you can get out of me than I've already shared. So the more people there are, the more questions there are, the more stuff that's going on. I'll try to get some cool, like, donut emoji things or whatever, and you know, it should be pretty awesome. You know, we'll get some fun stuff going on. Are there polls on here? Does anyone know if I can do, like, polls? Or no, maybe I'll just do that on Mastodon. Then you can follow me on Mastodon. I'll ask, like, who wants to hear about this or that or whatever. Oh yeah. Yeah, no, I'm really pleased that I was able to talk for 3 hours. Yeah, thanks again too for stopping by and checking it out. And I'm always happy to help with procrastination. This is productive procrastination because you're acquiring more mathematical experience and general knowledge from this. So you can always sell it to yourself that way. And for me, you know, I'm doing a lot of outreach, getting experience, you know, talking to people about what I'm doing. It's good for all of us. It's a good thing to do. Yeah, I mean, when I was an undergrad, maybe grad student, I used to think, you know, the University of Rochester would make a really great reality TV show, the math department in particular. But I don't know if that's realistic. But at least this is a good step in that direction, you know, where you're experiencing math happening in real life without any kind of, like, you know, filter of, like, people preparing things or, like, having a specific designated task to do or whatever. This is really more what it's like to just wander around in a math department and see what happens. Yeah. So yeah, I'm really thrilled with how this turned out. I really couldn't have asked for this to go any better. So yeah, thank you all so much. And yeah, is there any last quick question that anyone wants to know the answer to? Or anything like that? Well, you know, I have this really marvelous proof of a really astounding result but I won't be able to fit it into just the last little bit of this lecture or whatever. It's not really a lecture, but this live stream. That's what it is. Oh, okay, now that my joke is over, do I have any recommendations when asked to review a paper for a journal? Yeah, I've also done this. I've done this a couple times now, and like for conferences and for journals, and I guess I recommend that you try to do it if you can. I know that it's like free labor, and that's not the best. Publishing is a whole thing that I can't really address in the last little bit of the stream, but it is worth it. It does help the people. It helps your career. I assume you're trying to be some kind of academic. If that's what you're, that's what you're doing. I would do similar to what you do when you read a paper normally. I would kind of read over the whole thing first and then start going through and finding finer details. Oh, and remember, whenever they say it is obvious that, or clearly, or of course, blah blah blah, you gotta check that, because that's where they're trying to get you. That's where they're gonna try to pull the wool over your eyes, or maybe that's where they've deceived themselves, and those are the things you've got to check. Clearly is illegal. All right, well, it's 9 o'clock. I should probably go do something else with myself for a little while, maybe drink water, experience fresh air, that type of thing. But thank you all so much again for being with me. Thanks for watching this. If you're watching this on YouTube, it'll be posted there soon if it's happening live for you right now. And please check it out next week. I'll be doing the same thing, same time next week, same place, but different math, and it'll be cool. All right. Well, thank you all so much, and have a wonderful day or evening or whatever.